Do you have questions? No? I want to do this one example of a 3x3 system, and maybe that's it. I don't know what else to do. But consider this system: x plus y plus z equals 7, 3x minus 2y plus z equals 3, and x plus 6y plus 3z equals 25. So this is one of those 3x3 cases, and what we did on Monday, it is a good idea if we try to get two equations with two unknowns out of that, solve those two, and then go back, find the third variable. That's kind of what we're doing on Wednesday. Let's say I can use this first equation to kill the 3x and to kill that x. So then I'll end up with two equations with just two variables. I can solve that, and then go back, find x. Okay?
Did you always start with the first column?
No. Yeah, you can do that too. Yeah, that'll work too. But it's just because in this case it doesn't matter which one you do, because either you're going to be killing 3x or you're going to be killing 3z. So it doesn't matter. If we were doing matrices, which yeah, again, because you can always rearrange the order of equations. But with matrix, we always like to use this first term to start killing everything below it. And if it's just x without any coefficient, it makes it even easier. With matrices, even if there is a coefficient, you just divide everything by that coefficient, turn it into 1, it makes it easier to kill. But anyway, so the way we're going to do that, we'll just multiply the first equation by -3, right? And add it to second equation. So that is -3x minus 3y minus 3z equals -21, added together with 3x minus 2y plus z equals 3. So if I add these two equations, I'll just end up with -5y minus 2z equals -18. Right? Okay. And also I can kill x in the third equation. I can do this by going -1 times equation 1 plus equation 3. So -1 times equation, because I want to kill that x, right? So it has x and that has x. So I want to change the sign, right? So that will give me a -x, -y, -z equals -7. And the other one was x plus 6y plus 3z equals 25. So when I add these two, it becomes 5y plus 2z equals 18. Okay? So remember, this is my new equation 2, and this is my new equation 3. What? Yeah, kind of. So that leaves me with a little system, right? -5y minus 2z equals -18. And the other one was 5y plus 2z equals +18. This is the system that I wanted. System with two equations and two unknowns, but which you just noticed, if I start killing one variable, I'm going to end up killing the other one. So this whole thing becomes 0 equals 0. Well, now since that's in 3 dimensions, so we're talking about planes now, right? So there will be infinitely many solutions, okay, in this case, because we got an identity. But it doesn't mean that they all overlap. It could be that all the solutions along the same line, because right, if you just have 3 planes that intersect on the same line, that can happen. You can have 3 planes overlapping. I don't think that's the case here. Because I mean, these two, the last 2 equations are just multiples of each other, so they overlap. Okay, so that's really what happens. The last 2 do they overlap? No, they don't quite overlap. They're parallel. It's hard to see. No, they don't overlap. Yeah, it's hard to see. So there's probably going to have 3 planes that meet on the same line. Okay, but we can actually kind of still solve this system, because right now we can go further with that. Okay, but this case will have infinitely many solutions. And when we get that kind of an identity, we call these types of system, we call them dependent systems. Because these infinitely many solutions, there is still a rule amongst them. It's not just random triplets of values for x, y, and z. Okay? Because I can pick a variable, just any one of those 3 variables, x, y, and z, and I can express each solution in terms of x, y, and z. Okay, so let's say if I try to express everything in terms of z, for example, we don't have to do it in terms of z. We can do it in terms of any variable, but so what I can do then, I can take any one of these equations, let's say 5y plus 2z equals 18, and I can solve for y in this case, right? See what happens. How would you solve for y here? Right, subtract 2z, so it's 5y equals negative 2z plus 18. And then divide everything by 5. Y equals negative 2/5 z plus 18/5. Right? In terms of z. So I can also express x in terms of z. If I go back to my very first equation, x plus y plus z equals 7, and I can do the substitution, y is this now, I can solve for x in terms of z. So I just replaced y with the expression that we just found. So now we can solve for x in terms of z. I can do a little bit of simplification. If I combine 2/5, negative 2/5, plus 1, that's positive 3/5 z, subtract 18/5 to the other side. I mean, I'll have to do some computation, but right now x equals negative 3/5 z. I'm going to need a common denominator over there. So 35 minus 18. Right? So x equals negative 3/5 z plus 17/5. So that's the relationship between the three variables. So if I have my general solution to this would be x equals this, so negative 3/5 z plus 17/5. Y equals that, negative 2/5 z plus, what was that? Plus 18/5. And z is z, since we were solving for everything in terms of z. So any point that satisfies these conditions will solve that equation. So that's why we call it a dependent system, because it depends on the value of one of the variables. So if I just plug in value for z, whatever you like, then I'll get a point that solves that system. For example, if z equals 1, if I plug 1 in here, what do I get? So it's negative 3/5 plus 17/5, right? What does that give me? 14/5. Plug in 1 in here, so it's 16/5. And 1, z is 1. So here we go. So this point solves that system. But there are infinitely many points like that. You pick any other value for z. Let's say z equals negative 1, right? If you plug negative 1 in here, you're going to have positive 3/5 plus 17/5. So that's actually pretty 4, right? And you plug negative 1 in here, you're also going to get a 4, and z is negative 1. So that's another point that solves that system. Okay, so this rule right here allows us to generate infinitely many points that solve that system. And if you don't believe me, let's say this is easy to check. 4, 4, negative 1. Let's try that if I do that point. 4, 4, negative 1. If I plug it in here, 4 plus 4 minus 1 equals 7. That works, right? 12 minus 8 is 4, minus 1 equals 3. And then 4 plus 24, that's 28, minus 3 is 25, right? So that point solves this, all three of these equations. Same with that ugly fractional point. I don't want to do that one in my head. But that's the idea. So when you have that case where you start solving a system and you get to an identity, you can always still come up with the rule that relates each solution to each other. Okay, so this statement right here generate all those infinitely many solutions. Does that make sense? What? No?
Usually.
Partially. So any questions on this?
What is the point of this?
W-
Or why all those word problems we were doing?
Well, I mean, yeah, so there were just some examples where this comes up. I mean, you see, it's very rare that you're dealing with a world phenomena that only has one variable. You know, that doesn't happen like that. Every time you have many variables, but when you get into multiple variable situation, you're going to need multiple equations to find those types of solutions. Okay. Now, do you understand how we solve that? I mean, we started the way we were doing things on Monday, just starting with a 3x3 system and trying to reduce it to 2x2, and we got our 2x2 system. and the 2x2 system collapsed to an identity. Okay, so that was the big thing. So when we see that, we know we're dealing with a dependent system. So one variable depends on the other. So then when you start solving, we didn't have to pick z. I could have picked y. I could have solved for everything in terms of y. Wouldn't be a problem. I'll still get the same points.
How do you know which of the equations to use though? Because it matter.
That's what I'm trying to say. It doesn't matter. You see, if I do this, don't write any of that down. But let's say if I solve for y here. I'm sorry, solve for z. So 2z equals negative 5y plus 18 divided by 2, z equals negative 5 halves y plus 9. Right? I'd use this equation to solve for z. And then I'll go back to the first one, which was x plus y plus z equals, what was it, 7? And I plug this in for z, so that's x plus y minus 5 halves z plus 9 equals 7. So this is what? X minus 3 halves. I'm sorry, this is y, not z. Minus 3 halves y equals negative 2. So x equals 3 halves y minus 2. Right? So then my system is, the solution, x is expressed in terms of 3y minus 2. Y is y. And z was that, negative 5 halves y plus 9. Okay? So let's say I have this rule. Well, now if I start assigning values to y, I can generate the solution. Like, for example, before we got a solution 4, 4, negative 1. Y equals 4. So if I let y equals 4, and I plug 4 in here, 3 halves times 4 is what? 6. 6 minus 2, 4. Y is 4. If I plug 4 in here, 5 halves times 4 is 10. Negative 10 plus 9 is negative 1. So it still generates the same points, right?
But how do you know to start with that, like, the equation you started with and not pick one of the, like, other 5?
No. You mean the very first?
No, like,
Well, no. You have to pick one of these two that only have two variables. That doesn't matter. See, here I took 5y plus 2z. I could have taken negative 5y minus 2z. It would still give me the same thing. These two equations are the same. If I multiply the top by negative 1, I'll get that one. They're the same equations. Yeah. Because to find the third variable. Because this gives you the relationship between the two variables. So one variable, you just say, well, let's solve for everything in terms of z. Here I solve for everything in terms of y. If I were killing, as you were suggesting, why wasn't I killing z's to begin with? If I killed z's first, then I would have an xy system. Then I can solve for everything in terms of x. That doesn't matter. And again, as I was saying on Monday, there is no correct way of doing these problems, but they all should lead to the same conclusions. Like, see, we're generating the same points. So that's kind of nice, right? There's an easy point to do. Let's say if you let y equal 0, so what do you get? Negative 2, 0, and 9, right? If y equals 0 generates that point. Yeah, but that means if I let z equals 9 here, right? Z equals 9 on that point, right? The other two should come out to be negative 2 and 0. If I plug 9 in here, it's going to get really messy, but 3 times 9, what is that? 27, right? 27 minus, so negative 27 plus 17 is negative 10. Negative 10 divided by 5 is negative 2, right? If I plug 9 in here, so that's negative 18 plus 18, so that's 0 and z is 9. So it's still the same point, negative 209, negative 209. So it doesn't matter which variable you solve for. A lot of times, the solutions don't even appear with z's. They're just going to say, well, let's just call it a t, just a dummy letter. So everything is in terms of this magic t, but we know x equals this, y equals that, and z equals that. Okay? How's that? Is that okay? Well, that's about it. That's your course. This is the last thing I had to show you when you get dependent systems. That's an example of a dependent system. Do you have any questions for me?
So are we like doing a review next?
Yeah. Yeah, Monday, we can start reviewing now if you have questions.
You have my
Probably do. Right, because you didn't put your name on it. Nick, right? Yeah, here we go. I don't know. Is that a ooh good or ooh bad?
yeah.